Manual laundry once swallowed entire days of scrubbing. Electric motors and stamped galvanized tubs cut the machine's price from weeks of wages down to a few days. This is First Principles Daily, episode 73. Before the electric washing machine reached ordinary homes, a typical load of laundry demanded hours of lifting, soaking, rubbing on a washboard, wringing, and rinsing by hand. The labor itself was the dominant cost, measured in human time rather than dollars. Once manufacturers applied electric motors to drive agitation and used volume stamping to form galvanized steel tubs, the capital price of the machine itself fell sharply. That shift turned an expensive, specialized appliance into something a middle-income household could buy outright. For generations, laundry equipment stayed close to the manual methods people already knew. Washboards, wooden tubs, and hand-cranked wringers simply mechanized the same motions a person performed at a riverbank or in a washtub. Designers copied the shapes and materials of existing hand tools because those forms felt proven and required no new factories or skills. The finished devices therefore carried heavy wooden frames, individually formed metal liners, and separate hand-powered mechanisms that still needed constant human effort to operate. A typical early mechanical washer might sell for a sum equal to several weeks of factory wages, yet most of that price reflected the small batch fabrication of each tub and the assembly labor needed to fit the parts together. No one questioned why the tub had to be shaped by hand or why the agitator required a separate crank for each cycle. The convention simply reproduced the steps of hand washing at larger scale. Supply chains stayed local and fragmented, with wooden staves sourced one cooperage at a time and metal liners beaten or rolled in small shops. Because each machine was essentially a custom assembly of familiar components, the price remained high enough that only institutions or wealthy households bought them. The assumption baked into the entire trade was that laundry would always consume large amounts of time, so the equipment itself did not need to be cheap or simple to produce. That mindset kept the capital cost anchored far above the value of the steel, copper, and wood inside the machine. Even when early power sources such as water wheels or steam engines appeared in commercial laundries, the core geometry of the tub and the sequence of agitation stayed identical to the hand version. The goal was to scale the known process rather than to ask what forces actually had to act on the fabric. The result was a device whose every joint, seam, and linkage carried the accumulated labor of fitting parts that had never been designed to nest or align without adjustment. Owners accepted the high price and the ongoing maintenance because the alternative was still the full day of manual work. The machine merely reduced the physical strain without changing the underlying economics of production. Maytag and a handful of competitors began by asking what physical work actually had to be performed on the clothes, and what materials could deliver that work at the lowest cost once electricity was available. The raw material floor for a basic household washer consists of a steel tub, an electric motor, a simple agitator or impeller, a transmission, wiring, and a supporting frame. Commodity steel sheet in the early 20th century traded at a few cents per pound. A galvanized tub might contain roughly 40 to 60 pounds of steel, while the motor and drive added perhaps another 20 pounds of copper and iron. Adding the smaller quantities of rubber, wood, and fasteners produced a magic wand estimate around $10 to $15 in materials for an early electric model, though exact commodity prices fluctuated with wartime demand and regional supply. Under the old hand-built approach, the finished machine sold for several times that figure, yielding an idiot index that signaled most of the price resided in fabrication steps rather than in the atoms themselves. The first decisive change was the switch from wooden or riveted tubs to deep-drawn galvanized steel, formed on presses that could turn out hundreds of identical shells per day. Stamping eliminated the skilled labor of fitting staves or welding seams and removed dozens of leak paths that had required hand caulking. Next came the integration of a fractional horsepower electric motor directly coupled to a simple gear or belt drive, replacing the separate hand crank and its associated castings. Because the motor could run at constant speed, designers could replace multiple valve and linkage families with a single cam or timer sequence, cutting part count and the hours needed to assemble and adjust each unit. Galvanizing the stamped tub in a single dip further reduced corrosion worries and allowed thinner sheet without sacrificing durability. Each of these moves attacked a specific slice of the old idiot index. Stamping attacked forming labor, the motor attacked human time input, and the simplified drive attacked the number of custom machined pieces. The trade-off that had to be won was reliable electrical insulation and safe starting torque. Early motors were therefore deliberately overbuilt with heavy copper windings until insulation materials improved. Once those process problems were solved at scale, the same presses and winding machines could serve many thousands of machines, spreading their capital costs across volume. A natural objection is that electricity itself was not universally available, yet the redesign still lowered the machine's price even in regions where power arrived later, because the capital cost of the device itself had already been compressed. Another objection is that stamped steel might dent or corrode faster than thick wood, but the galvanizing layer and the ability to replace a damaged tub quickly offset those concerns for most buyers. The arithmetic becomes clearer when one compares the labor hours. A cooper might spend half a day shaping and fitting a single wooden tub, while the press produced the same volume of steel in minutes. That ratio, repeated across thousands of units, is what pulled the finished price toward the material floor. By the late 1920s, a basic electric washer from Maytag or its peers sold for a price equivalent to a few days of average wages rather than weeks, and ownership spread rapidly into working households. The new idiot index sat far lower than the hand-built predecessors because the dominant costs had moved from skilled assembly into the repeatable operations of stamping and motor winding. Even so, the machine still required a separate wringer, manual filling and draining, and regular maintenance of belts and seals, so the labor reduction was only partial. The physical floor remained limited by the need for a pressure-tight tub, a reliable motor, and enough structure to survive decades of vibration. No redesign could eliminate those elements without changing the task itself. Later automatic models would attack the remaining manual steps, but the early electric galvanized machines already demonstrated how volume processes could compress the gap between material value and finished price. One limit that persisted was the requirement for a separate power source and water supply. In homes without indoor plumbing, the machine still demanded significant setup labor, so the full benefit appeared only when paired with other household infrastructure improvements. The idiot index could not drop to 1 because the motor windings, the gear reduction, and the final assembly still added value beyond the raw commodities. Yet the index had already fallen from the double or triple digits of the hand-built era into a much narrower band. A tub that once required a cooper and a riveter to assemble now emerges from a single press stroke because the designer treated the shape as a repeatable steel shell rather than a wooden barrel. An agitator that once needed a separate crank for each load now receives its motion from a motor whose windings are laid down by machine, showing that the cost lives in how the motion is produced, not in the motion itself. The same logic of asking what work must actually occur and which process can deliver it at the lowest material multiple applies to any product whose price still reflects custom fitting instead of repeatable forming. Tomorrow the show returns with another concrete case or an industry whose numbers still sit far above their physical floor. Which everyday object whose price feels fixed would shift first if someone rebuilt it from the atoms upward? That's a wrap on today's First Principles breakdown. The ideas travel further when you pass them on. Send this to a fellow builder. I'm Patrick in Vancouver. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at Nerra Network. Links in the show notes. This show comes to you from the Nerra Network. If you want another sharp daily briefing, Modern Investing Techniques has you covered. Modern strategies for Canadian and US investors. All our shows are free at nerranetwork.com. Live dashboards, TSLA, SpaceX launches, the investing scoreboard are all at nerranetwork.com data. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own.